Hello everyone, and welcome to this fourth webinar in this series on electrical machines. Today's webinar will focus on some very basic underlying principles of electrical machines, and we will be trying to explore and understand that why do electrical machines produce torque in certain conditions, and eventually we will also see that how exactly the equivalent circuits are derived. So the equivalent circuits, we will be looking at them from the first principle, and we'll try to establish that it is possible to derive the equivalent circuits using the basic fundamentals of electromagnetism. So with that, I would like to start my webinar today, and I welcome you all to this webinar. Now, before we go deeper into the webinar and into the topic, we'll start with some of the very fundamental things about our induction synchronous machines. So here, if we see, and we all know very well that synchronous machine produces torque if and only if the rotor rotates at the synchronous speed. So the speed of rotation of the rotor should be same as the speed with which the field produced by the stator winding rotates. That means the relative speed between the stator field and the rotor should be zero. So that's the condition which has to be fulfilled to produce torque in synchronous machine. Now, before we go into the details of how things work, let's have a look at a 3D animation of the synchronous machine. Now, this animation is actually designed to show that how the internal features of a synchronous machine look like. So this machine is being dissected here, or rather deassembled, and each and every component is being removed in a sequential manner to give some idea of how precisely the synchronous machine is made and what are the constituent components of the synchronous machine. What we see here now are the two slip rings which are being removed. These are the connections between the external power supply and the rotor coils. Now the outer cover is removed, and eventually the coils of the stator are removed. And here we see the insulation layer between the stator and the stator coils is being removed, and eventually here we see that the rotor coils were removed, and this is what we have as the rotor shaft. So this is a very short version of the video 3D animation that is present in the actual book, so it has been shortened keeping in mind the limited time that we have for today's webinar. Now, if we look at the synchronous machine and try to understand how exactly the torque is produced, then we see that the torque produced in the synchronous machine is given by the expression over here. So this is the general expression of discussion about the synchronous generator, its excitation system, so we'll not dwell deeper into it. This is not the topic that we are going to discuss today. So we come here and we see that the torque produced by the synchronous machine is given by this expression. So this is the expression 8.1a. Here we see that the torque is proportional to the stator current, that is the magnitude of the current that flows through the stator coil, and IR is the magnitude of current that flows through the rotor coil, and max is the mutual inductance between the stator and the rotor coils, and delta is the angle between the magnetic fields created by the stator and the rotor current. This angle is also known as the load angle. So this is the general expression of the torque produced by the synchronous machine. And today we are going to see that how exactly this torque equation originate and what are the underlying principles behind this torque equation. Moreover, it would be very interesting to see that how the torque equation for an induction machine look like. And here we see in expression 6.3b, the torque produced in the induction machine is given by multiplication of the air gap field into BR into sine delta. So this gap field is the field produced by the stator windings, we can say, and BR is the magnetic field produced by the rotor windings, and delta is the angle between the stator and the rotor magnetic field. This assumption is valid because during the normal operating condition, when the slip of the machine is around 1% or around 1%, then the air gap field is predominantly due to the stator current, and the rotor's magnetic field is quite small. However, if the rotor magnetic field is substantial enough, then this B gap is not just the field produced by the current in the stator coil, but it is the vector sum of the field produced by the stator current and the rotor current. So whatever resultant magnetic field that we get is known as B gap, and we take the product of that with the air gap magnetic field, rotor's magnetic field. So BR is the rotor's magnetic field and gap is the air gap flux density. Both the magnetic fields exist in the air and they have an angle between them, delta. So how does it come and so on? So that's a topic of different discussion. So it's explained here in chapter 6 in great detail, and maybe we will have a look at this equation more carefully. But the point that I wanted to bring to your notice is that if you look at both the equations, so the equation that we saw for the synchronous machine and the equation that we see here, in both the cases we can see that the nature of the equation is very much similar. You see, in case of a synchronous machine, the torque was expressed in terms of the stator and the rotor current and the mutual inductance between them and the angle between the magnetic field produced by the stator and the rotor currents. And in case of an induction machine, our magnetic field is again product of the air gap field, the field produced by the rotor current in the air gap, and the angle between the gap, B gap and BR. So if you see here, the nature is very much similar, and now from this one can get an idea that there is an underlying principle between the torque equations of all kinds of machines. Now to understand that in deeper, what we do is we go back to one of our very early chapters, so that is chapter number 3, and have a look at the system where we have a singly excited machine. So in this machine, what we see is that we have a stator, and the stator has coils wrapped around it, and the coils are fed from a single phase AC source of certain frequency. And the rotor is a ferromagnetic piece, and it has saliency. So if you see here, the stator has saliency and the rotor has saliency, and there are two axes on the stator. One is the D axis, and this D axis of the stator is aligned along the stator poles, and then we have the Q axis of the stator, which is actually perpendicular to the D axis of the stator. Similarly, rotor has two axes, A and B. So the A axis of the rotor is along the longer side and B axis is perpendicular to the A axis of the rotor. So this is the general configuration of the machine that we have, a simplest rotating system. And through this we will start our analysis of how exactly the machine operates. So if we look here very carefully, then we can see that there are two extreme positions of the rotor possible. So one extreme position of the rotor is shown here in figure 3.22a. So in this position, the A axis of the rotor coincides with the D axis, and in the second extreme position, the A axis of the rotor is perpendicular to the D axis of the stator. And from here one can understand that once we have the configuration shown in figure 3.22a, the reluctance seen by the stator flux. Now you can see here, since there is only one excitation, so the operating flux would be created by the current flowing through the stator coil. And if we see the reluctance that the stator coil, the flux produced by the stator coil will see is smaller in this case, when the orientation of the rotor is as shown in figure 3.22a, and the reluctance seen by the stator flux is larger when the orientation of the rotor is as shown in figure 3.22b. And that's quite simple, because we can see here in this case we have a larger air gap, so the flux line has to cross a much longer air gap, and then a shorter ferromagnetic path, and then a longer air gap. But if we see in this configuration, the flux lines have to follow a very small air gap, and then a longer path in the ferromagnetic material, and then again a shorter path in the air gap. So the reluctance felt by the flux lines is smaller in case of 3.22a and is larger in case of 3.22b. So from this it is clear that as the rotor moves, the reluctance that the flux lines produced by the current in the stator will be changing continuously, and hence the reluctance is a function of rotor position, and that is what is expressed in expression number 3.58 over here. So if we see, as the rotor keeps on changing its position, which is represented by angle theta r, the reluctance would vary, and the variation of the reluctance is shown in figure 3.23. So in figure 3.23 we see the variation of the reluctance, and this is very nicely illustrated in this animation over here. As the rotor keeps on moving, the reluctance seen by the stator flux keeps on changing, and the reluctance observed by the stator flux is shown by, or is represented by, the red dot which moves over along the curve. So this red dot keeps on moving along the curve depending on the rotor position that we have, and here the rotor tends to move in a clockwise direction. So now if we look at the torque produced in this case, so the torque produced would be given by this general expression of torque. So it's quite understood, or I'm sure most of you would be knowing, that the electromagnetic torque produced is equal to minus rate of change of field energy at constant flux linkage, or it is equal to rate of change of co-energy with respect to angular position of the rotor at constant current. So both the expression give us the torque expression. So for our discussion here, we'll be considering the first expression over here, which is the rate of change of torque with rate of change of field energy with respect to rotor position. So the field energy that we have in this case is actually changing with rotor position because the reluctance is changing. Now this is an interesting point that we have to keep in mind. As the reluctance changes, the inductance would change, and if the inductance of the system changes, then the energy stored in the system would be changing. In principle, the energy stored in the system in an inductive system is half into inductance into current square, so it's half Li square. Now as the reluctance changes, L changes, and as the L changes, the stored magnetic energy or the field energy, which is WFLD, that would keep on changing. And here we can see from this animation that as the rotor moves, the reluctance changes, and as the reluctance changes, the inductance would change, and as the inductance would change, the field energy would change. Hence we can conclude that in this simple machine that we have, the field energy would be a function of rotor position, and if we take its derivative, it turns out to be the quantity or the expression which is given here in 3.59. So 3.59 gives a torque expression for this simple machine where we have only one excitation, which is on the stator. Now let's assume that the stator is excited by a sinusoidal voltage source. So the current flowing through the coils would also be sinusoidal in nature, and let's say that that current produces a flux which is also, of course, which also would be of sinusoidal nature, and it's represented by phi m cos omega t. So phi m is some magnitude of the flux, and the variation of the flux is cosine over here. And we also represent our angular position of the rotor as omega rt, which is the angular speed with which the rotor is moving, minus angle delta. So this minus angle delta is the initial position of the rotor. So the meaning of initial position, or the way the initial position can be measured, is the angle between the d-axis and a-axis of the rotor. So initially, this initial angle delta determines that what was the position of the A axis of the rotor with respect to D axis. So the angle measurement can be clockwise or anti-clockwise depending on whether the rotor rotates and clockwise or anti-clockwise. So this is the meaning of this angle delta that we can see here in expression 3.61. So now what we do is essentially we replace phi, which was given in the previous equation 3.59, with phi given in equation 3.60, and we replace theta r with omega RT minus delta. So after substituting all this quantity theta r and phi into the torque equation, so we end up with the final torque equation, which is given by expression 3.62 over here. Now this expression 3.62 can be expanded since it's a trigonometric it involves trigonometric quantities. So the trigonometric expansion of the torque equation 3.62 gives us this equation, which is given by 3.63. So this is the expanded form of the torque equation. Now this equation is something where we have to pay attention. If we see this equation very carefully, then there are three sinusoidal terms, and all the three sinusoidal terms are functions of time t. So this torque expression actually represents the instantaneous torque. By instantaneous torque we mean what is the torque produced at different positions of the rotor, at different angular displacement of the rotor. Now if we want to find out the average torque produced by the machine, then we would have to integrate expression 3.63 over a time period. And since each and every sinusoidal quantity that we have in this expression 3.63, all the three sinusoidal quantities are functions of time, and if we integrate this expression over a time period, the average value that we are going to get is 0, because the average value of a sinusoidal waveform is 0. So this is the reason why the average torque obtained from expression 3.63 would be equal to 0. Now in order to get non-zero torque, we will have to satisfy certain conditions, and those certain condition in this case, I'm sorry, not conditions, rather one condition, and that condition is if we make the rotor speed, the speed with which the rotor rotates, if we make that equal to the angular frequency of the applied voltage, then what happens is we are essentially making omega r is equal to omega. So if we see carefully in this equation 6.63, the last sinusoidal term becomes independent of time t. So if we make omega r is equal to omega, then the last term in equation 3.63 becomes independent of time, whereas the first and the second sinusoidal term in the expression 3.63 would still be dependent on time, but we will have one quantity, one sinusoidal term, which is the third term, which would become independent of time. Now once it has become independent of time, and if I take the average value, that means I integrate the expression of torque over the entire cycle, over an entire period, then I would end up with a non-zero average torque value. So from here we can see that in case we want non-zero average torque value, then the condition that we must satisfy is that the speed of rotation of the rotor should be equal to the frequency of the applied voltage to the stator coil. So this means in principle that the machine that we are investigating is a synchronous machine, because the magnetic field of the stator changes its position at a speed of omega radians per second, and the rotor also moves at a speed of omega radians per second. So the rotor speed is same as the supply frequency. So in this case, this machine is a synchronous machine, and the average value of the torque is given by the expression 3.65 over here. So we can see that the average value of torque is now a non-zero quantity, and it is dependent on angle delta. So if we see here, if the angle delta happens to be 45 degree, then we get maximum torque. If angle delta is 0, then we get 0 average torque, and in case the angle delta is 90 degree, then again we get 0 average torque. To understand this, we will have to go back to the initial figure, which is figure 3.22a and 3.22b. So figure 3.22a represents the condition when the angle delta is 0. That means the a-axis of the rotor coincides with the d-axis of the stator. And here if we see, this is a position of stable equilibrium. So to start with, if this is the position in which the rotor was lying, then the machine will not be able to produce any non-zero average torque. And if similarly, if the machine rotor is oriented as shown in figure 3.22b, this is also a condition of equilibrium. Although it's not a stable equilibrium, but it's a condition of equilibrium. So here if we see, the b-axis of the rotor coincides with the d-axis of the stator. So the angle is 90 degree in this case. Okay, so with the angle that we measure is the angle that the a-axis of the rotor makes with the d-axis of the stator, and this happens to be 90 degree in case of figure 3.22b, and this is also a condition of equilibrium. So in neither of the two conditions that we are seeing here in the figure on the left and the right, the machine will be able to produce an average torque, non-zero torque. To produce non-zero torque, this angle delta should not be equal to 0 and should not be equal to 90 degree. It can be anything else in between. And of course, the maximum value would be when the a-axis of the rotor makes an angle of 45 degrees with respect to the d-axis of the stator. So in that condition, the machine will produce highest average torque. That means the point when the machine starts, the initial position of the rotor should be such that the a-axis of the rotor makes an angle of 45 degree with respect to d-axis of the stator, and hence the machine will be able to produce maximum average torque. And the variation of the average torque is given here in figure 3.24. So at 45 degree we get maximum average torque, and at 0 and 90 degree we get 0 average torque. Now since we also discussed that the reluctance is related to the inductance, and that relation is given here in expression 3.66, so my d-axis inductance is n square by reluctance along the d-axis, and LQ is n square by reluctance along the q-axis. So if I substitute that in the previous expression of torque, so I can, that is the expression of the torque that we have in 3.65. So if I replace the reluctances RQ and RD by inductances using expression 3.66, then I can represent my torque equation as given here in expression 3.67. Similarly, we can do the analysis further, and we can also represent our flux phi m in terms of current flowing through the stator coil, and hence we can get the torque expression in terms of current. So because you see the flux produced by the stator coils is a function of the stator current as well. So this flux phi m can be also represented in terms of stator current and number of turns that we have in the stator coil. So this was in short the description about the torque produced in a simple singly excited system. Now to understand this analysis further, what we do is we jump to a doubly excited system. So the doubly excited system, the simple doubly excited system is shown here in figure 4.3. So if we look at the figure 4.3 very carefully, then we see that there are two coils. One coil on the stator, which is excited by an AC source Vs, and then we have another coil on the rotor which is excited by an AC source Vr. So we have two coils and both the coils are excited by a separate source. So this is a system which is closer to most of our machines. So in principle, both our synchronous machine and asynchronous or induction machines are doubly excited systems in principle. They are doubly excited systems because there are two magnetic fields. One magnetic field created due to the current flowing through the stator coil, and we have the other magnetic field created due to the current flowing through the rotor coil or bars in case of induction machine. So since there are two magnetic fields created in the air gap, these machines are in principle doubly excited system, even though induction machine is supplied only by one source. That means the stator is given an excitation generally in case of an induction machine, and always in case of wound squirrel cage induction machine. Even though a squirrel cage induction machine is excited only by giving a source to the stator, it still is a doubly excited system because there are two magnetic fields created. The current flowing through the bars of the rotor also creates a magnetic field in the air gap. So the doubly excited system means that there are two magnetic fields and there are two currents, one in the stator and one in the rotor. But before we go further, let's have a look at this system. So this is our simplest doubly excited system, and here what we have is a very interesting animation for you to see that how exactly such kind of systems are made. So if you see here, we have a rotor, a salient pole rotor, which is being punched. So these are the laminations of the rotor, and then they are punched to give a shape, the desired shape, whatever shape we want, and with that a number of laminations are made, and all these laminations are stacked together and the complete rotor is created. So the rotor is in principle laminated. And similarly, if we look at the stator core is also laminated. So here we can see various or a large number of stator laminations being created and being put together. So once we have the desired number of laminations, depending on how long the stator is, these are then stacked together and eventually they are compressed to make the stator core. And this is how eventually the system looks like. So we have one coil on the stator and then we have one coil on the rotor, and the rotor coil is fed through slip rings by a source, and similarly the stator coils are fed by an AC source. So that was a very short version of the animation that we have shown. So the book contains the more elaborate version of the animation. So due to time shortage, we are not going to show you the complete animation of the entire system. So it's just an idea of how the system actually looks like. So now let's come back to our system, the doubly excited system. And if we look at this system very carefully, there would be three torque terms. And to understand why there are three torque terms, so let's go back to the figure of the doubly excited system. So if you see here, the stator has saliency and the rotor has saliency. So if we consider the case that there is no coil on the rotor, so that's same as the previous case of a singly excited system, and as the rotor rotates, the flux created by the stator current will see a changing reluctance, and due to that we will have a torque production, which we saw in the previous section. Similarly, if we assume that the stator has no coils and only rotor is excited by an AC source, so as the rotor rotates, the flux produced by the current flowing through the rotor coil will also see a changing flux, a changing reluctance, and due to that we will have reluctance torque being produced. So if we see here in this equation 4.17, so in figure expression 4.17, there are three torque terms. The first term is due to the change in reluctance seen by the flux produced by the current in the stator coil. The second torque term represents the change in the reluctance seen by the flux produced by the current flowing in the rotor coil. And the third torque term is due to the interaction between the stator and the rotor magnetic fields, and this interaction takes place due to the mutual inductance between the stator and the rotor coil. So if we go back to the figure and see, if the rotor rotates here in figure 4.3, then the mutual inductance between the rotor and the stator coil will keep on changing, and that mutual inductance would be a function of the rotor position. So for example, in this case, as shown in figure 4.3, the axis of the rotor coil coincides with the axis of the stator coil, so the mutual inductance is maximum. If this rotor rotates by 90 degree, the axis of the rotor coil and the axis of the stator coil will become mutually perpendicular, and hence the mutual inductance between them would be 0. So we can see that as the rotor rotates, the mutual inductance between the two would keep on changing continuously, and that's why we have this MSR, that is the mutual inductance between the stator and the rotor coil, and that is a function of the rotor position. The self-inductance of the stator is a function of rotor position. We have seen that as the rotor rotates, the reluctance seen by the flux produced by the stator coil will change. Similarly, the self-inductance of the rotor is also a function of the rotor position, because the flux produced by the rotor coil will also change as the rotor changes its position. So from here we can see that the torque consists of three quantities. So the first quantity is the torque or the stator reluctance torque, the second quantity is the rotor reluctance torque, and the third quantity is the interaction torque. Now after having understood this, what we can see here is an animation. So in this animation we see that both the stator and the rotor have coils and current flows through them, and as the rotor rotates, we can see that how the flux lines see a different reluctance. So as the reluctance seen by the flux line changes, so would be the orientation of the flux lines. So the orientation of the flux lines would also change. So this animation shows that both the stator and the rotor coils are excited. And here we see that as the rotor rotates, the reluctance seen by the stator flux would change, and this is what we have seen already. So it would be kind of a sinusoidal variation of the reluctance. Similarly, in this animation we can see that the rotor has no excitation. It's only the stator which has coils, and that those coils carry current. So as the rotor changes its position, the flux lines which are created by the stator current see a changing reluctance, and that is the reason why a reluctance torque is being produced in this case. And here is the third animation. So if we see this animation very carefully, then the stator has no current, it has no coils. The rotor has coils and current flows through the rotor coils, and due to this the flux is produced. And we see that as the rotor rotates, the flux produced by the rotor coil sees a change in the reluctance, and this is responsible for the reluctance torque of the rotor. So this animation 4.4 shows the reluctance torque, why the reluctance torque exists if only the rotor is excited. And then we have here the animation 4.3 shows that why do we have stator reluctance torque, and the animation 4.1 shows that why do we have interaction torque. So here you see in 4.1 both the stator and the rotor coils were excited and the fluxes interact, and hence torque is produced. So by these flux lines one can get an idea that why do we have different kinds of torque being produced in this doubly excited system. Now let's consider the scenario if we replace the salient rotor by a cylindrical rotor. So here we can assume and we can understand very well that if we neglect the stator, okay, and we assume that there is no current flowing through the stator coil. We do have the stator core, but there is no current flowing through the stator coil. And if the rotor coil is excited by a current source, and as the rotor rotates, it is going to see a changing reluctance. Okay, and whereas if we assume that no current flows through the rotor and it's only the stator coil that is being excited, and as the rotor rotates, we would see that the stator flux will not see a changing reluctance. So this is the case. If we just excite the stator coil and change the rotor position, the reluctance seen by the stator coil, which can be seen here, does not change. So you see here, rotor carries no current. It's only the stator which has coils and carries current. So as we keep on rotating the rotor, the reluctance seen by the flux lines don't change. You see, the flux lines remain more or less constant, and hence in this case there will be no reluctance torque due to the stator. However, if we consider a configuration shown over here, so here the rotor has a saliency and the stator has no saliency. So in this case, if we excite the stator and give no excitation to the rotor, then we change in the rotor position, we would be experiencing a change in the reluctance. So this is in short about when and where the reluctance is produced. And now I think we can skip this discussion further and we proceed to the case that we were going to discuss today, which is the torque produced in the machine. So our synchronous machine that we have seen was a salient pole machine, was a non-salient pole cylindrical rotor machine that we saw the animation at the very beginning. Similarly, our induction machines are also cylindrical rotor machines. So we'll focus our discussion on the cylindrical rotor machine. So a simplest cylindrical rotor machine is shown here in figure 4.8. So if you see here, stator has one coil and rotor has one coil, and the angle between the axis of these two coils is represented by angle theta r, and that is also the rotor position. So the rotor position is measured in terms of displacement between the axis of the stator and the rotor coil. So if we see this very carefully, this figure, as the rotor rotates, the mutual inductance between the stator coil and the rotor coil will keep on changing, and that change in mutual inductance is shown in figure 4.9, and that variation is a cosine variation. It's a cosine variation because we have assumed that initially the coil of the stator axis coincides, the axis of the stator coil coincides with the axis of the rotor coil at time t is equal to 0 initially. So in that case, we have the maximum mutual inductance, and then as the rotor rotates, the mutual inductance keeps on changing, and the variation is shown here in figure 4.9. Now after having seen here the animation, and this animation shows that how the mutual inductance changes as the rotor changes its position. So this is just an animation to help us visualize how the variation of the mutual inductance takes place. And here in this box, the complete detailed explanation is given, so I will not be going into the details of this, so one can actually have a look at it through the book. And let's go back to our discussion. So here what we do is, initially we assume that the stator is given a current of frequency omega sc and of magnitude is, and the rotor is given a current of magnitude ir and frequency omega rc. And let us assume that the rotor rotates at an angular speed of omega r, and initially the rotor position was such that the angle between the stator coil and the rotor coil was delta. So this is the initial angle of the rotor, and this initial angle of the rotor is the angle between the coils of the stator and the rotor, and that also is the angle between the magnetic field of the stator and the rotor. Okay, so the magnetic field produced by the stator coil will lie along its axis, along its coil axis. Similarly, the magnetic field produced by the rotor coil will lie along the rotor axis, and the angle between these two axes is the initial angle of the rotor, and that is represented by angle delta over here. Now we can see from this configuration of the machine that there is no saliency. There is no saliency in the stator and there is no saliency in the rotor. Now since there is no saliency, the flux produced by the stator current will not see any change in reluctance as the rotor moves. Hence, no reluctance torque due to stator. Similarly, the flux produced by the rotor current will not see any change in reluctance as the rotor rotates. Hence, no reluctance due to rotor. So with both these two reluctance torques out of the discussion, the only torque that we are left with is the interaction torque, and that interaction torque in this case is given by expression 4.25. So from expression 4.25 we can see that the interaction torque that exists in this configuration is product of the stator current, the rotor current, and the mutual inductance between the stator and the rotor coil, and we have the terms involving the stator frequency omega sc, rotor frequency omega rc, and the rotor speed omega r. Now this torque expression can be simplified using the trigonometric identity shown in equation 4.26. Now using this identity given in 4.26, we can simplify expression 4.25 and we get the expression for the torque over here. Now if we look at this expression for the torque given in 4.28, we see that it consists of 4 sinusoidal quantities, and if we look very carefully, all the 4 sinusoidal quantities are functions of time. So this torque expression gives us the instantaneous torque. Now if I want to find out the average torque, I would have to integrate the expression 4.28 over a time period, and if I integrate expression 4.28 over a time period, then we are going to get 0 average torque, since each and every quantity is a sinusoidal quantity and it's a function of time. So if we integrate a sinusoidal function over a time period, we get 0 average value, and this is the reason why we are going to get 0 average torque from equation 4.28. However, to get non-zero average torque, we can make either of the 4 coefficients of time 0. So if I make the first coefficient of time equal to 0, that means omega sc minus omega rc plus omega r is equal to 0. This is one condition. If I have this condition, then the first term in this torque expression 4.28 will become independent of time, and the remaining 3 would still be functions of time. And if I take the integral of this over a time period, integral of this torque expression over a time period, I'll get non-zero average torque. Similarly, we can have 3 other conditions which will ensure that if we integrate equation 4.28 over a time period, we will get non-zero average torque, and all these 4 conditions are summarized here in equation 4.29 and equation 4.30. So from these 2 equations we can see that if any of the 4 conditions are satisfied, there are 4 conditions. If you see this, there's a plus and a minus outside the bracket in 4.29 and 4.30. So in total we have 4 conditions. If either one of the 4 conditions is satisfied, then we get non-zero average torque. And let's see how. If we satisfy the condition that omega r is equal to omega sc minus omega rc, And if we take this condition and substitute that in equation 4.28, then we are going to get a torque expression given in equation 4.31a. And here we see the second quantity, the second sinusoidal quantity becomes independent of time. And now if I integrate this torque expression 4.31a over a time period, I would get a non-zero average torque. Similarly, if I take this second condition, then I would be reducing my first sinusoidal quantity to be a function. I'll convert my first sinusoidal quantity into I'm sorry, I would actually be eliminating the first sinusoidal quantity from being a function of time. So my first sinusoidal quantity will no more remain a function of time if I use this condition. If I use the third and the fourth condition, I can see that I'll always get one sinusoidal quantity which is not a function of time. And if we take the average value of the torque from all the equations, that means if I take the average value of torque given by equation 4.31a or 4.31b or 4.33a, 4.33b, all of them are going to give me this average value of torque. And this average value of torque will be non-zero if my angle delta happens to be not equal to 0 or 180 degree for that matter. So in this case, in this simple machine that we have seen with two coils, there are two conditions that are necessary to ensure non-zero average torque. First is that we should satisfy either of the four conditions between the frequencies, that is the frequency of the stator current, frequency of the rotor current, and the angular speed of the rotor. And the other condition that has to be satisfied is that angle delta should not be equal to 0. And these conditions are actually satisfied by all machines, AC or DC. Okay, be it a series DC motor, separately excited DC, shunt excited DC motor, or be it a synchronous motor or a synchronous generator or a salient pole synchronous machine or an induction machine, both squirrel cage and wound rotor. So all machines satisfy this condition. So this is the underlying feature of all electrical machines. Now to understand this better, what we do is we try to do an exercise. So this is a really very intuitive exercise that we have developed. So it's again a doubly excited system. Stator has one coil, rotor has one coil, as we have seen in our discussion so far. So this is an example based on this configuration which is shown in figure 4.8. So if we see here, the stator, sorry, it's not based on figure 4.8, rather it was on in chapter, in the earlier part of the chapter. I'm sorry about that. Let me just go back to the figure which is represented by this example. So it is this, yeah, figure 4.3, a doubly excited system. So if we see here, the stator's self-inductance varies as 3 plus cos 2 theta, so some variation of the stator self-inductance, and similarly the rotor self-inductance varies as 30 plus 10 cos 2 theta. So this is for the system which is shown here in figure 4.3, and we have the variation of the mutual inductance which is 0.3 cos theta. Now let's try an exercise. Let us assume that the current through the stator is 10 ampere. The current through the rotor is, let's say, 5 ampere. I assume that my rotor rotates at a speed of 3 radians per second. My stator supply frequency is 5 radians per second, and my rotor supply frequency is 1 radian per second. So let's do some calculation. So it says that first we have to calculate the rotor. I give an initial rotor angle, let's say 45 degree, and we do the calculation. So first we have to find out the angles, rotor angles, as a function of time. So we know the rotation speed of the rotor, it is 3 radians per second. So and the initial position of the rotor happens to be 45 degree. So based on that we can calculate rotor angle in radians and in degrees. So in the actual problem in the book one has to solve and fill in the values, but here since we are running short of time, so I'll just fill the values automatically, but in the real problem one has to fill in these values. So here you can see we get the rotor angle as a function of time. Then what we do is let's go to the next step. Here it says that calculate the stator self-inductance. Now stator self-inductance is given by the expression 3 plus cos 2 theta. So theta we have already calculated, and we keep on substituting the values of theta and find out what is the stator self-inductance. So since we don't have much time, so I will not be typing the values. I would rather fill them completely automatically. So here we have the variation of the stator self-inductance. Then we go to the next step, and this says that calculate the rotor self-inductance. The rotor self-inductance is given by 30 plus 10 cos 2 theta. So theta is already calculated, and let me just fill, and here we get the variation of the rotor self-inductance. So let's go to the next step, which says calculate the mutual inductance. So mutual inductance is given by 0.3 cos theta, and here the theta is already calculated, and I fill the values, and here we see the mutual inductance. So mutual inductance can assume negative values, whereas the self-inductance of the stator and rotor is always positive. It cannot be negative. Mutual inductance can be, because if we have two coils whose axes are 180 degree apart, then they will have a negative mutual inductance. So now let's go to the next step.